go through the presentation to stay on schedule. This is what I'm going to talk about, some basic terms in technology. Then there's a main MPLS application, or I call it application, that's MPLS VPNs. Those exist in two flavors. There are so-called MPLS VPNs, which are kind of basic layer 3 technology, and there's another thing called layer 2 VPNs. And from this layer 2 VPNs, there's a special flavor called VPLS, which is very interesting and promising technology. We will see that widely deployed in the future, and I'll give some insight how it works and where possible security implications will arise. Just a word to my person. I like to call myself an old school networker. That's I prefer to work on layer 2 to 4, to work with devices and protocols. I'm not very good as it comes to operating system security or buffer overflows or things like that. I prefer to stay in the network layer with a special focus on security since many years. And in 2001, I founded a company or a group of people covering IT security topics, which is located in Heidelberg, Germany. I'm the CTO and I'm the founder, but I'm a bit away from the administrative and management stuff. I try to focus on technology. I'm the author of a book about pen testing, and I'm a regular speaker. I try to share knowledge, and I try to discuss topics, and that's why I'm here. I hope you will learn a bit from my presentation, and I will learn from other presentations, and we will be able to discuss those things. As for the basics, MPLS stands for multi-protocol label switching. It's a switching technology mainly used for forwarding packets based on labels. So packets get something added, the so-called label, and this label is responsible for the forwarding of the packets. The initial goal was to have a more efficient forwarding technology than IP-based routing, which is not very efficient for several reasons. And MPLS is used in most carrier, if not all, carrier backbones. And it's a basic technology, and it serves as a foundation for something called advanced services. The label itself, the main technical part here, it's a 32-bit structure which can be split up into several parts. The most important part is the so-called tag. This is, you can call it the label itself, the thing that is responsible for forwarding. There's a time to live, and there are some experimental fields and the so-called bottom of stack, but this is not too interesting for us here. The most interesting part is the tag, is the label, which is a number which is added to a packet. As for the mechanism, how it works, usually there's some kind of MPLS-enabled backbone consisting of devices that are able to speak MPLS. When a packet arrives at this backbone, it gets classified due to some parameters. The most important one usually is to the destination prefix, so destination of the packet, and according to this destination it gets a label, but it can also be according to a customer. If this is customer A, it gets a label 20, and if it is customer B, it gets a label 21. I'll get back to that later on. After the classification and labeling, the whole forwarding is done based on the labels, and these labels are swapped at each hop. So the labels don't remain the same in the whole path here. This is usually done, or this is mostly done to avoid some central label administering mechanism, some label database or whatever. So two hops negotiate about the labels and their meaning to them. When a packet leaves the whole network, the label is removed and the packet gets forwarding in a kind of classical way and routed based on IP destination address. This is the basic technology. When we talk about security here, whenever you hear about technology used for forwarding or routing packets, the first thought usually is, okay, can I inject or can I spoof those labels? This can be done, but it does not have many use. As I said, those labels are negotiated locally between 2 points. So even if I manage to modify a label, I won't be able to modify the path of a packet beyond the next hop, as there are 2 other boxes who have negotiated. We do not gain much here by label spoofing or modifying. But I already said MPLS is used for so-called advanced services. So these labels can serve many other purposes. Amongst these services, there is something called VPNs, layer 2 and layer 3. There's a technology called Any-Transport over MPLS, in short, ATOM. A special flavor of that, VPLS. There's something called MPLS traffic engineering, mainly used by providers to optimize bandwidth usage in the backbone and optimization of paths. And there's even something called generalized MPLS, GMPLS, used for signaling and optical networks. So there are many different uses for MPLS, aside from this basic technology with labels to get forwarding paths. You can see it like this. There's some kind of network structure, no matter what, no matter based on what technology. Put MPLS on it, and you can profit in several ways. This is the way providers or carriers see it. Many of these technologies are relevant only for providers. That thing, for example, that thing called traffic engineering. But others, those VPN services, can be used, are of big use for organizations, usually as customers. You buy some MPLS-based VPN service from your customer, or organizations can use it themselves on campus networks as a kind of, let's call it, modern VLAN technology. I've been working in several big group companies which use MPLS in their backbones to segregate traffic between subsidiaries based on the same campus. This is the technology most widely deployed, so-called MPLS VPNs. It's an MPLS-based technology. It uses labels, which is no surprise for something called MPLS-based, but it's got its own concepts and terminology. It can be compared to frame relay or ATM in some respects. It's a highly virtual technology, so you imagine kind of backbone, and you use this backbone, whatever it is, for some traffic separation, traffic segregation. You don't need something like ATM switches or frame relay switches or whatever. Just one infrastructure, no matter, and put MPLS and put VPNs on it. The most important thing here is there are additional labels that are used to establish logical paths or circuits to segregate traffic between customers. Customer A traffic, customer B traffic, crossing the same shared infrastructure, but separated in some logical way by means of the labels. It's a very flexible technology. It's widely used in the meantime. To get some basic terms and technology again, usually there's a distinction between the backbone run by a provider. This is called the P network, provider network. There are devices in here, the PE, provider edge routers or the provider backbone routers. And there are devices running at the customer side, operated by the customer itself or by the provider. Those devices, which are the edge connecting the customer network to the backbone, are called the CE routers. During transport across this network, 2 labels are used. One to identify the egress PE, means if a packet gets in here, and this one knows, okay, the packet should leave the network at this place or another place. And another label to identify a particular customer. You'll see this in more technical way soon. The provider edge routers usually handle several customers, can connect lots of customers, and to distinguish between their traffic and their routing, in the PH router there are kind of logical routing tables called VRFs, virtual routing routing and forwarding instances. Aside from this, every PE has a global routing table, and it has a routing table for every customer. A more complex view is this one. What you should get from this display is the information, which customer is connected to which PE and with what addresses, is shared or is exchanged across the backbone by so-called multi-protocol BGP. That's an extension of BGP used to transport information about labels and customer sites. This has the advantage that several customers can use the same IP addresses. There will be no conflict if they use the same IP addresses, as there's a routing based on that virtual routing table, and the information about these virtual routing tables is exchanged by extended kind of BGP. What happens in detail? The PE routers, those boxes here, assign labels to prefixes per VPN. Those labels are called route distinguishers. This information is exchanged between the PEs by multi-protocol BGP. I'll show this in more detail later. So one PE usually knows which other PE is responsible for a given prefix in a given VPN. This PE is responsible for forwarding traffic for the yellow customer to the network 10.1.00. And this PE, for example, is responsible for forwarding traffic to the green customer side in network 10.1.0.0. When a packet leaves an ingress PE, the packet has two labels, one for transport across the backbone and one for the VPN. So the whole VPN thing is done based on these labels. The labels are responsible for segregating traffic here. There is, talking about security, there's a kind of official point of view. This is an old MIRCOM study validating Cisco MPLS-based IPVPN as a secure network. You get the statement already from the headline. Most of you won't believe MIRCOM studies anyway, but this is kind of the official point of view. We should be a bit skeptical about this one. You should at least consider there's no encryption. So if your understanding of the term VPN was that there is mandatorily some kind of encryption protecting confidentiality or integrity, this is not the case here. So maybe your term VPN should be renewed in some way. The PE device usually is shared with other customers, which may have security impact. If one customer DOSs the device, it may take down other customers too. Usually internal audit does not like these facts too much. I'm a bit kind of emotionless here. I take it as it is. You just have to know this. And usually you should do some risk assessment then, if it's appropriate for the traffic you want to transport by this means or not. But these things are not too new anyway. Talking about attacks is much more interesting. There are 5 kinds of attacks which I'll name here, given it's a VPN technology. Interesting attacks include eavesdropping, so violating confidentiality and or authorized access, getting into networks. I personally do not find DOS too interesting. Those attacks can be divided into 2 kinds of attacks coming from the outside, so from a customer or from the internet, and 2 other attacks coming from the inside. And there's an attack that's not dependent on MPLS. That's attacks against management boxes or management tools. If you get access to the provider box managing all those VPNs, you can probably modify the VPNs and modify the traffic paths. But this is not particular to MPLS. Let's start talking about those attacks. The first one was injection of labeled traffic from a CE. So one customer tries to insert or inject packets that get to another customer's network. According to the RFC 2547, which is the most important one here, labeled packets are not accepted by backbone routers from untrusted or unreliable sources. And a customer side, as per definition, is an untrusted source. So a PE router should not accept packets arriving from CEs which already have labels. It's a PE's duty to assign those labels. It should not accept packets arriving that already have labels. We did some tests. I have a big lab with Cisco devices, and this seems true. It's not. I did not encounter any case where it was possible to inject labeled packets from the outside, from a customer side. So what about injection of labeled traffic from the internet? Maybe those PE routers are available from the internet anyway, as they serve other functions too. So what if an attacker in the internet tried to get into some VPN by sending labeled packets to a PE? This usually would require the attacker should know IP addresses and labels used to be able to introduce the packets, which usually is not too difficult. In most networks, you can assume there's some infrastructure device sitting with an IP address of 10.111. In most networks, such one exists. And those labels are usually assigned in a way that can be predicted on most boxes. So it's not too difficult to guess labels and IP addresses. The more interesting part is you should be able to reach a PE or a P router from the internet, which depends on the design of the network on the provider. And you should be able to get the packet through, packet with a label through to that box, which depends on several parameters. It's not clear if this works. But given the RFC, such packets should be discarded anyway, as they come from an untrusted origin, namely from the internet. I made a lot of tests. This seems to be true. However, there are two prominent people working at Cisco, and they wrote a book about MPLS VPN security, and they state this attack is possible under certain conditions. I was not able to reproduce, but they say it's possible. So maybe it would be possible to get into a VPN via the internet. I was not able to get this work. This is a tool another German guy released some weeks ago that's used for label brute forcing. Can be found here. This tool can be helpful for this kind of attack, to find out which labels are used in some structure to be able to inject traffic then. The tool itself, I've not tried it yet. It's rather new. The more interesting thing here is that we are currently at the state that tools start to emerge. Those attacks are no more completely theoretical, but there are guys out there writing tools for those attacks. So we will see interesting things here in the future, I predict. The third attack was modifying that exchange of multi-protocol BGP amongst those PE boxes. If you can get into this exchange, you could probably modify, for example, the sites belonging to a VPN. You can add a site to a VPN. An attacker controlling a box in a provider backbone may be able to generate a new customer site in a given VPN and to participate in that VPN. This requires access to the core, to the MPLS backbone, which is debatable. I'll talk about this in more detail later. It requires the right tools at point of attack, which may be difficult as a point of attack is a router and you can't install packet injectors usually on a Cisco router or Juniper router, which are the two main vendors here. But given we'll probably see more controllable kind of routers in the future. This may be possible. Another problem is the BGP information is not updated regularly. They only exchange it once. So to modify this information, one must either withdraw the current information and inject a new one, or intercept the initial exchange, which will be rather difficult as from a protocol and from a packet view. But this, at least theoretically, this is possible, and this would offer lots of opportunities to get into a VPN. This is how the exchange looks like. Usually the information is, dear colleagues, if you try to reach this prefix in this VPN, please send me your packets with this label attached to it. Means a router who originated this information will forward packets into this network at this customer side if it receives a packet with label 18. Next one is modification of label in the core to insert packets into VPNs. So just modify the traffic flow, modify a label, and by this be able to take packets from customer A and get to customer B's VPN. This requires access to the core. This requires, again, right tools at point of attack. But point of attack may even be a box inserted, or a box which gets traffic rerouted, or a box at the provider side. If these requirements are met, the attack itself is easy. I'll try to show it practically. I've set up some SSH sessions. I hope they still lived. This looks good. This one too. I hope you can still hear me, even if I'm okay. Seems to work also. And I need this one. Just to explain what I'm doing now is, imagine this attack scenario. There's a yellow VPN and there's a green VPN, and the attacker has, by whatever means, access to the core. I will have a simple ping flowing in the yellow network, and I'll modify it on its way, so a box in the green network will receive the echo response. Then, okay. This is the box an attacker controls to give you an impression how this things with the labels work. Show IP, BGN, VPN. Okay, I should give this a bit more space. Okay. What's happening here? I don't see the... you can see here, this is a box, that's the PE box that serves two VPNs. One VPN is alpha and the other VPN is beta. And in the alpha VPN, there's a network 172.31.10. And in the beta network, there's the same VPN. This is one of the advantages of this technology. Customers may use the same addresses. They don't have to renumber or whatever. And for this traffic, the label 17 is used, and for this one, label 19 is used. We will be able to see this. So when a box from VPN alpha pings across the backbone, we see there's traffic arriving at this PE with a label 17 attached. We will be able to see this traffic by just sniffing it. Okay. So now we see the whole traffic that is exchanged between those two PE boxes, which is mainly at the moment LDP, hello messages. LDP is the label distribution protocol, the protocol they use to negotiate about labels or to just to inform they are still alive. We will see some OSPF there. We will see some BGP, all this infrastructure stuff. I will now sniff this traffic and record it. And ping again. So I should be able to see this ping crossing the backbone. Okay, here we have all that infrastructure stuff. I'll delete some rows, and here I see the ping, and after this I see the ping, the echo reply. I'll modify the echo reply to re-inject it with another label, to re-inject it into another VPN. The most interesting part here is this is it's Ethernet based, the lab I'm running here. So Ethernet source and destination addresses. Here's the snap type used for MPLS 8847, and this 3 bytes here are the label. There's only one label at the moment, as the other one has already been popped. It's already been removed, and these 3 bytes indicate a label. And the label itself is the upper 20 bits. So this one and this one are the lowest bit and the 5th bit. So this one, this 17 can be found here, and this one and this one here. So just modifying, I should be able to get into another VPN. I'll modify it to a free one, as the other VPN is using a 19, so there's the bit consisting the 2 is set. This should be all I must do. So I've now constructed the packet, which should be able to get into the other VPN. Before I re-inject that packet, I have to disable the span port. This box is sitting on a span port on a device. At the moment, it can only receive traffic. It can't inject traffic. I have to disable the span port then, which should not be the case. Depends on the point where the attacker sits and what the attacker is able to do. Okay, the monitor session is disabled. I should be able to re-inject the packet then. You should have a look at this window here. This is the other VPN. There's a box sitting. I just turned on ICMP packet debugging. Basically, show me all ICMP packets arriving or passing through this router. I'll even go back to that one. We hopefully will see the labeled packets again. So if I try to re-inject the packet now, I first have to convert it to hex. Input file is temp packets. Output file is temp packets in binary format. And now just re-inject the packet. Okay, and you see, it's always a good feeling when a demo works during a presentation. And this one worked. We now see a packet arriving with label 19 at the box, and this box, situated in a completely different VPN, received the echo reply. So I was able to jump across a VPN boundary here. Okay, thanks for that. I continue then. I have hopefully other interesting stuff in my presentation. So to conclude here, label modification and subsequent VPN hopping can be done. It is possible to traverse VPN boundaries here. It's a one-way street though. It can only be used to get packets into VPN, not to establish packets flowing back and in one direction and back. It can only be used for stateless attacks, for example via SNMP. For the next time I'll give this presentation, I prepared it. How to inject a label SNMP packet, and to get a configs router written to a box controlled by an attacker. Or for UDP-based worms, for anything that does not require backward traffic. You should know this attack will go completely undetected. There's no checksum in the packet, which includes the label. Modifying IP headers will usually require modifying the checksum too, or at least some checksum errors. Some IDS boxes could be aware of this, or checksum errors. But in this case, MPLS, the customer B will by no means able to know this was an injected packet. So this works. Modifying the other attack, modifying multi-protocol BGP packets may even offer a road to more efficient attacks, but they are much more difficult to perform. Both attacks require access to core, which is a topic for lots of discussion amongst the provider personnel. I work a lot in provider environments. In most security discussions, the core is assumed to be trusted. I assume most people here in the room are a bit cautious about it's assumed to be trusted anyway. So we should be skeptical here. This sounds a bit naive. However, I tend to agree. But you should know this thing is more and more used in campus networks. There is no provider-run or provider-operated backbone. It's operated by IT people there, which not necessarily have too much knowledge about securing MPLS or things. There are two other things. Providers may be connected via IXPs, Internet Exchange Points based on switched infrastructures. Get access to a switch there, and you will be able to at least modify VPNs amongst or across those providers. Things like that exist. There are VPNs based on provider agreements. And you should at least know it's not impossible at all to hack into a provider box. This is from NANOC meeting in 2003. A statistic, compromised routers only in ISP environments. This is not customer-based routers, it's ISP-based routers compromised in the statistics. And it all depends on correct configuration and operations. There may be people who make errors. Anyway. Another thing to note, attacking VPNs from within the core was possible with frame relay and an ATM as well. Usually I'm asked, okay, what's the point here? This is true, but you have to know at that HS there were dedicated devices, frame relay or ATM switches, and not multifunction, big, mainly IP-oriented routers, which in provider parlor we call them hybrids, which have a lot of functions. Amongst those functions serving VPNs. And there was a protocol world besides IP then. and IP-based attack tools. You ever heard of LibNet for ATM? I didn't. But there's LibNet for IP, and the LibNet is able to create MPLS packets. The tool I showed the main page of was, in fact, it's based on LibNet. So it's not no more the same world, and these are not only theoretical but very practical attack paths then. I'll come to the next technology. That's the so-called layer 2 VPNs. This usually designates another mechanism or technology called any transport over MPLS, in short ATOM, which is used for the transport of different layer 2 protocols across a MPLS backbone. It's not IP packets that are transported, but it's now ATM cells or frame relay frames or Ethernet frames, which get as a whole transported across the backbone. This can be very useful for providers or customers for various reasons. It operates with something called pseudo wires, kind of logical circuits, again, established between MPLS-capable backbone devices. The inner workings are roughly the same as with layer 3 VPNs. Packets have two labels, one for forwarding purposes, one for to identify customer side. There may be some additional parameters I won't cover here. Modifying labels should allow VPN hopping as described above, so no difference here. Get into the core, manage to modify labels, and you will be able to get to other people's VPNs. But there's another thing or another aspect which is interesting, which applies to mainly these two technologies, Ethernet over MPLS and virtual private LAN service. To give a brief introduction, this is Ethernet over MPLS. You can imagine as just the customers are connected, or the customer sites are connected via Ethernet to a PE box, and they throw in Ethernet frames, not IP packets, maybe even SNA packets or whatever, layer 3 protocol or even IPX, if used anymore. And this is tunneled through the network, and what gets out here is Ethernet again. So the sites, they have the impression they are connected directly together. This is very interesting for customers, and lots of providers already sell this kind of stuff. The problem here is this only provides point-to-point connectivity. If there's another third site, you have to establish a tunnel to the first site and establish a tunnel to the second site, which is not very scalable if you regard 50 or 100 sites big customers have. This is why another technology was invented called VPLS, Virtual Private LAN Service. This is mainly the same with the big difference that it's multi-point. So you can connect different sites, and they have an Ethernet connect here. And for all of them, they seem to be connected directly. What happens here is that these PE routers have to exchange whenever a site joins. There has to be some exchange mechanism, which is still discussed, which one this will be. But when it's established, those sites have the impression they are connected directly together. The whole cloud, the whole MPLS cloud, is then often regarded as a big switch. I prefer to see it as a big trunk. It's not a big switch, as it does not take part in switching infrastructure operations as STP or things. But at least you can have a switch here, a switch here. These devices may be switches. And it seems that those two switches are connected directly. Maybe you already get an idea why this is a very promising or interesting technology. For customers, there's no more distinction between layer 2 and layer 3. Just sites connected directly, spitting all those Windows broadcasts across the backbone. But there are a lot of network admins who like the idea of this, and I too do. To speak about security again, we have to refresh some characteristics of Ethernet. Ethernet is a broadcast medium. There's MAC learning on switches, on the forwarding devices. There's a flooding of certain frames, multicast or broadcast frames, or frames with unknown destination MACs. there has to be some loop avoidance, usually by means of a spanning tree protocol. There's something called VLANs, and there is technology, Cisco parallel called trunks, and HP parallel called tech pods, to connect the VLANs and to connect the whole thing. If somebody like this should be implemented, the infrastructure must emulate all these technologies. It has to provide the whole Ethernet functionality across the backbone. I'll skip this. This a bit would take too much time here. Just take as a note. There are several things still unclear or still not discussed for the final state of this technology. But I have a hypothesis here that is implementing Ethernet via WAN technology, in this case MPLS, will create a whole new bunch of challenges in terms of network security. The current state of affairs is carriers do not sell transparent Ethernet. So customers do not get real Ethernet. Even if there are carriers, I can't judge for the US, I can only judge for Europe. One of the biggest European carriers I worked at, that was Swisscom, they sell something called carrier Ethernet service. You can connect several sites just by Ethernet, no more WAN technology. But you can choose your VLAN numbers then. The provider gives it to you. It says you can only use VLAN 10, 20, and 30, and another customer uses VLAN 40, 50, and 60. This is not what customers want. So carriers will have to offer real Ethernet. This is at least what I expect. And this is already the case in vendors' implementations. For example, in Juniper's VPLS implementation, the whole cloud behaves totally transparently. So imagine that the whole MPLS cloud was providing something like a transparent Ethernet thing. We will see interesting things then. I assume some basic layer 2 protocol knowledge. Feel free to ask questions after the presentation. In Ethernet, if those two sides are connected via an MPLS backbone with running VPLS or Ethernet over MPLS, there has to be a spanning tree route. There will be only one, and it will be elected at one site. This is not surprising. This is the way STP works. But what if a customer wants redundant connections? And customers do want redundant connections. They do not want to be dependent on one connection which can fail. Then STP will have the effect depicted here. STP route is elected here in the site New York, and in the site Amsterdam, the inter-switch links connecting the switches in the whole site will be going to blocking state, as the route is here. Some of you may already have a bad feeling when seeing this, but from a security side, one can state that this is a network problem. It's a protocol problem. STP behaves as designed. So what's the security point here? Imagine this thing's happened, and it's network behavior as designed. It is, in fact. Maybe this is a network thing, but does corporate IPsec realize, or internal audit, that Bob's access to this file server, Bob's sitting here, the file server is sitting here, in reality passes the MPLS backbone as the STP route is here. And the whole thing, remember, is done unencrypted. There's no confidentiality protection in MPLS VPNs. There's no confidentiality protection here in any way. This box may be located in another country, and maybe in that other country something like Carnivore applies, or at least a different understanding of intellectual property may exist. If this guy has access to some construction things or trade secrets located on this box, maybe is not aware that these things go to some part of the world where intellectual property has a different meaning. There's one problem. Another one will be VTP, Virtual Trunking Protocol. Remember that Cisco, and old Cisco, you moved to a small site some years ago. You already forgot this box existed, but this box had a function in the network before. And now, as the sites get connected across the backbone, you will remember it when it melts down your whole network, as it holds a higher VTP revision number. This is a typical Ethernet problem. Most people doing layer 2 know this, but most are not aware this will happen across a backbone, which is supposed to be a layer 3 then. What about VLANs? Imagine you had inside Amsterdam, you had a VLAN 10 called servers, and inside Paris you had a VLAN 10 called wireless LAN. They have nothing to do with each other in a layer 3 world. Now running VPLS or Ethernet on MPLS, Paris will be able to see this VLAN. It's VLAN 10, it's VLAN 10, so they are connected directly together. And those people participating here in the wireless LAN will at least see all the Windows-based broadcasts, and they will be surprised, okay, what is this? Maybe I should just take an address from that space, and I can see all the Windows-based servers here and connect to them or attack them directly. Problem here is in most organizations there are organization-wide IP addressing plans, so layer 3, but no organization-wide VLAN structures, layer 2, which is important here. All these may be network problems. It's totally consistent protocol behavior, but they do have security impact. This is what is interesting here. It's not it's no new problems, but new problems that will convert it to another world here. And always remember, there's no encryption. PE devices are shared. So we consider all this stuff. Talking about attacks, there are two classes of attacks in the age of VPLS. That's attacks over the cloud or attacks against VPLS devices. As for attacks over the cloud, if the cloud is, they depend on the level of transparency the cloud provides. Given full transparency, and this is, for example, what Juniper does at the moment. I've been working with a big Juniper testbed with VPLS. You can perform any classical layer 2 attack over the cloud. I tested this successfully with Yersinia, which is the most important layer 2 attack tool. And from my side of view, I'm a networker, but a networker with special interest in security. This is pretty cool. Sitting at one side and up-spoofing and sniffing boxes located in a geographically wide, far away wide site. This is rather interesting what we will see here from an attacker's point of view. Hack a box here, and you will be able to do all that fancy layer 2 stuff with the other sides. Attacks against VPLS performing devices. Again, they depend highly on the functions they perform. Remember that image, VPLS cloud can be regarded as a big switch. I do not agree. I prefer to see it as a big trunk, as the most, they do not talk layer 2 protocols like spanning tree, those boxes. Many layer 2 attacks will not be feasible then, but they have to perform at least one, at the first glance, minor function of layer 2. That's they have to learn and store MAC addresses. One box has to know one PE device. If I have traffic for another MAC address, do I hand it over to that PE or to another PE? To the PE in New York or to the PE in Seattle? This brings us back to a usually very lame attack, MAC table flooding. In most pen tests, I do not even try. It's an attack from another age, some kind of, but it gets some rebirth here. kind of. This is what I saw in a testbed. The testbed consisted of Juniper M7i routers. You have to know these are considered big iron. These are provider routers. The empty chassis costs, I think, $20,000 and equipped with some interfaces. They range from $50,000 to $100,000. Provider equipment, and I had a test bed with 6 of them, and they just sat around, did nothing. They were just connected, did not transport any traffic, any production traffic, just a test bed. And in this state, CPU utilization was at 2% of the switching engine. I put out macOF. Most of you certainly know, part of the DSNF suite, rather old Mac flooding tool. And I just flooded, I connected the laptop to one side and just started flooding with macOF. With an old laptop, I have this one, I have another one running FreeBSD, which is 4 years old. I threw out packets, and the CPU usage went up to 11%, as there's a maximum of 512 addresses to be applied. But this won't suit many customers, 512 boxes at one side. So the providers have to adjust that, and they won't adjust that based on a customer or individually for every customer. This customer has 800 boxes at this side and 1,200 boxes at this side, so we put in 900 here and 1,300 here, but they will adjust to the maximum. This is usually how operations in providers is done. When you adjust it to the maximum, just throwing in with one laptop, I was able to bring up the CPU utilization to 25%. Maybe this seems to you, okay, 25%, what's so special about that? The first thing you have to know, Juniper devices, when you work with them, they are rather stable. You can't really shock them, and you cannot introduce failures by overflowing them or overloading them, usually. But this is very interesting. Big iron, big, expensive devices doing nothing, which are supposed to support thousands of customers with this kind of service. And I sat there with a laptop, and I could bring up to 25%. This is, for somebody who worked with Juniper, this is very surprising. It's a sign they did not really understand maybe the converging of layer 2 and layer 3 here, and what they have to support and what problems will arise. Back to my hypothesis, implementing Ethernet Wire 1 technologies will create new challenges in terms of network security. You get the idea, I hope. What can or what should be done if you want to use such technologies, those layer 2 technologies, get familiar with filtering on layer 2. The whole filtering stuff will go down one layer. If you are used to run a network with routers and devices with access lists on layer 3, this will disappear a bit, and the filtering should go down one layer. You have to define responsibilities, and you should at least closely monitor the things passing through the CE devices and the backbone. Summary of my presentation: MPLS is not just a forwarding technology, but serves as a foundation for several advanced services also. Amongst those services, there are different VPN technologies. Under certain conditions, these may be attacked or security problems may arise, so just perform risk assessment. Be aware of the technology and understand it and understand where the risks lie. There are new technologies emerging that provide something like Ethernet services across MPLS clouds, and the subsequent merger of layer 2 and layer 3 will have broad implications for our understanding of network security, our current understanding. Questions at this point? I'm here the full 2 days, so if you...
Would you use the VPLS?
Sorry?
Would you use VPLS considering all the issues?
Well, it depends on the advantages it could provide for my network. Yes, I would. And I know of several customers that would too. I gave this talk at Black Hat Europe, and after the talk, somebody asked the same question as you. Do you think anybody will use this? And several hands in the audience raised and say, "Hey, this is cool. This is interesting, and probably we will use this. We will see this. This is my my hypothesis." In some years, there will not be that distinction between layer 2 and layer 3 we have at the moment. It will a bit disappear.
Is it really, how effective is it compared to just using smaller average speech facility?
You get rid of the whole layer 3 stuff. You don't have to. You've just Ethernet. You don't have to operate boxes with layer 3 interfaces.
Bridge in each office?
Sorry?
You just have a bridge in each office.
Yes, it's a kind of bridging them. You will have to, if there are in big organizations, the network people are divided. Okay, those responsible for the switches and layer 2, the campus, and those responsible for the layer 3 stuff, the routers, the uplinks. This distinction will appear. You won't need it anymore. You just have Ethernet. Just plug it in and it works. But be aware of these things. Any other questions? If not, thanks for your time.